So in the previous lecture, we wrote down the max flow problem, treated it as the dual, looked at the DRP, and I just finished by saying that a solution to the DRP, which is what we're going to use to improve, is this augmenting path that is has a special property. So let's just summarize that. So what does the primal dual algorithm do? It improves the dual solution F, which seeds this whole process, by finding an augmenting path, which means a path that's going to augment the flow. So this is going to be an undirected path. So a path that is not just restricted to using edges in the forward direction, but it's going to be an undirected path that is restricted in the following way. Restricted to use an edge in the forward direction only if that edge is unsaturated in the dual solution that seeds the process. So in other words, Fij strictly less than Bij. And using an edge in the backward direction only if that edge had strictly positive flow, Fij strictly positive. This is kind of let me draw like kind of a simple example here. Let me try to do it on the fly. Let's find a kind of an orientation, and let's say this is, capacity 1, capacity 1, capacity 1, capacity 1, capacity 2. And let's say that I'll write down the solution in a different color. Just a solution. Doesn't have to be an extreme point, doesn't have to be an optimal value. So this is, from S to T. And let's suppose that I put half a unit of flow here, half a unit of flow going up here, 0, 1/2, and 0. Whoops, and 1. Okay, so let's say that's my solution. Then we can see that what's happening. Let me choose yet another color. I can't put more flow in this direction. That's not going to work. Okay, but what primal dual is going to do is note that I could actually push more fluid this way. This is an augmenting path, and it is, you can see intuitively that it's going to work. Right? This should become 1, this should stay 1, this should be 0, and if that's 0, then I'm going to have an extra 1/2 here. So we can see that that's going to improve. But I just want to make sure we understand why this is an augmenting path. So I'm allowed to use, let me erase that and just talk about it. Whoops. So let's talk about why this is an augmenting path. I am allowed to use this edge in the forward direction because it's not saturated. I'm allowed to use this edge in the forward or backward direction because it is unsaturated. Its capacity is not 1, but also it's 0. This edge I can only use in the forward direction because it's at 0. So this counts as an augmenting path. And how am I going to use it? If I use it, I'm going to use this in the forward direction. I'm going to use this as in the backward direction, and this in the forward direction. So by sending epsilon flow through this augmenting path, I'm going to increase the flow of any edge that was used in the positive direction. Hence, I can only choose non-saturated edges. I'm going to decrease the flow of any edge that I use in the negative direction. Hence, I can only use edges that had strictly positive flow, so we're able to be reduced. And then yeah, so it's those two things. So how much can I increase my how much can I increase in this case? How much can we increase? So in other words, P nu is going to be, I'm using P, but I guess I should be using F since we're talking about flows. F nu is going to be my F old plus theta times my solution F bar. F bar is going to have negative entries now. So I'm going to increase theta until I satisfy with equality a previous constraint that I was satisfying without equality. What are the constraints that we can satisfy with equality? These are our two constraints. Our flow conservation constraints are always satisfied with equality, as we've discussed. So basically theta, we increase theta until one of two things happens. One of the edges used in the positive direction saturates, or one of the edges that we're draining, like this edge, hits 0. Okay, so this is the basics of what an augmenting path is and how we're going to use it. Okay, so that's good. I hope that explains a little bit better what an augmenting path is. A key is going to be the key question. I mean, this is a clear that this is going to improve F, but an important question is, why, when this process stops, why, when we cannot find an augmenting path, do we know that we're optimal? So, key question here is, what happens when we cannot find an augmenting path? We know that the answer is that we're feasible. We must be optimal, but we want to see why, because we've stepped a little bit outside the primal dual setting exactly. We could of course just appeal to that, but we want to tie it back closer to that. And then one of the other things that's going to fall out of so we know the answer here is that we must be optimal. And one of the keys to seeing that is going to be another major algorithm result, which is actually very easy for us because we've already shown strong duality. And that is, from LP duality, a key to answering this question, which we're going to see in the next slides, is the relationship between max flow and min cut. So this is where we're going. And so before we get to the details of how we find this augmenting path, obviously in more interesting settings than what I can just draw and eyeball the solution, and in order to bring this link to max flow and min cut, we need to talk about what a cut is. Okay, so definition is as follows. In a graph, V with S and T, a source and a sink, an ST cut is a subset of the nodes subset W of the nodes such that S is in W and T is in its complement, which I'll denote by W bar. So note that sometimes a cut is also defined as a subcollection of edges. But in this case, I'm just defining a cut as a partition of the nodes into two, where S is in one piece and T is in the other. So I'll just write this as a note. A cut is also sometimes defined as the edges, as a set of edges between W and W bar. So one piece of terminology that is pretty common, and also we're going to use it later down the line, so I might as well introduce it here, is delta minus in a directed graph. Delta minus of a node V is the set of edges, directed edges or arcs, terminating in V. So everything that points to V. Similarly, delta plus is everything pointing out of V. And I can use this as I can generalize this to a collection of nodes to be all edges from W to W bar. So all edges originating outside of W bar and ending up in W bar. So this is the definition of a cut. We're going to be in this lecture talking about a cut as a subset of nodes, and I can also talk about the capacity of a cut, which I will denote as C of W bar, and this is just going to be the sum of the capacities of all of the edges going from W to W bar. So this is the sum over all ij such that I is in W, j is in W bar of B, I, j. Okay, this is the cut. So now we're going to look at back to our max flow LP, and we're going to look at its dual, and you can probably guess where we're going. The dual, the solutions to the dual of the max flow LP is going to be cuts. So the max flow LP, once again, we've seen this now a number of times, max V, subject to AF plus DV equals or less than or equal to, as again we've discussed, these are equivalent, so we just write whatever is more convenient. F less than B, F greater than 0. Just for form, before I wanted it to really look like the dual of a primal, so I wrote it as minus F less than or equal to 0, but this is the same thing. And again, remember that D is this vector where DI is equal to minus 1 if I is S, plus 1 if I is equal to T, and 0 otherwise. So now, what is its dual going to look like? I'm just going to write it down, but again, good practice just for you to write this down. I have a constraint here for every node, and I have constraints here for every edge. So I'm going to have dual variables that correspond to nodes. That comes from these constraints, and dual variables that correspond to edges that come from those constraints. So the dual of this is going to be a minimization problem. So it's going to be a minimization sum. I'm going to use gamma ij to be the dual variables that correspond to these constraints that have to do with edges. And you can see that my dual variables that correspond to nodes are going to have a 0 in the objective because there's this 0 here. Subject to Pi minus Pj plus gamma ij greater than 0 minus Ps plus Pt is greater than 1. Gamma ij is non-negative and P is free. So just practice, make sure that you feel comfortable with that being the dual. The main point I want to make in connection to the previous slide is that if we're given a cut, we can define a feasible dual solution. So given an ST cut W bar, again S as in W, T as in W bar, we can define gamma ij equals 1 if I is in W, J is in W bar. So gamma ij is 1 if the edge crosses and 0 otherwise. And pi is going to be 0 if I is in W and 1 if I is in W bar. So so look at that and look at the dual, and it doesn't take much to convince yourself the following: that any of this, that a cut defines dual variables just like I showed, and it is a feasible solution. So perhaps I need to let me try to bring that over onto the next next slide here, so I don't save myself some time in copying, since we have technology. Whoops. Okay, so here is my dual variables. I'm talking through this while I just rearrange things quickly. So sorry, my cut and pasting here has I've run into more trouble than this was worth, because it moves the okay, so here's my dual solution. Hopefully everyone, sorry, here's my dual, and here's my dual solution, and you can see, you can check that that indeed this it's easy to check feasibility. So easy to check dual feasibility. But a key point I want to make is, because again, what we so a key point is that when is any of these inequalities going to be tight, or when is it going to be strict for any dual solution defined from a cut? P I minus pj plus gamma ij, we know this has to be greater than or equal to 0, but this is going to be strict only when I is in W bar, J is in W. Because in that case, we're going to get 1 minus 0 plus 0, which indeed is going to be strictly greater than 0. So all of the constraints in the dual are going to be satisfied with equality for any dual solution that comes from a cut, except for constraints that cross from W bar backwards into W. Okay, so now that we've written down max flow and its dual, we can appeal to LP duality to write down this basic result, which is a fundamental result. It just happens to be easy for us now that we have LP duality. So the theorem says that the value of an ST flow is upper bounded by the capacity of any cut, that's an ST cut, right? For any cut, for any ST cut. This is weak duality. So we certainly know that this is immediately true. And moreover, what strong duality tells us is that max flow equals the capacity of the smallest cut, and therefore the flow F and cut and whatever cut we have are jointly optimal if and only if the cut and the flow satisfy complementary slackness. So part of the spirit of this class is complementary slackness has nothing to do with combinatorial optimization, but we're going to get a structural understanding of what complementary slackness means for this combinatorial problem. So what does complementary slackness tell us here? It says that Fij has to equal 0 for any arc or edge ij such that I is in W bar and j is in W. Again, where did that come from? This was the point on the previous slide, that this inequality in the dual is going to be strictly positive whenever we have an edge going from W bar to W. Therefore, Fij, the primal variable, has to equal 0 in that case. And similarly, Fij has to be saturated, has to equal Bij for every I, J in E such that I is in W and J is in W bar. This is just complementary slackness. So we're going to next use this in order to give the Ford Fulkerson labeling algorithm and a proof that when Ford Fulkerson terminates, it's guaranteed to have terminated at an optimal solution. So we're going to pick this up next.